Okay, week 8, part 1. So for these notes, we're kind of reviewing things we've already talked about, but I'm trying to spell it out very clearly. So with the block sliding down the inclined plane, there's two ways for me to explain this to you. And one way is to sort of go through why that's the case. So that's what I'm doing here. The weight pulls straight downward. So we break that down into components. This is called the parallel component because it's parallel to the surface of the plane, parallel to this surface. And then this is called the perpendicular component for the same reason. So with the free body diagram here, we basically have, I have it drawn right here. So the free body diagram ends up looking like this, where the force down the plane ends up being mg times sine theta after you SOHCAHTOA on this triangle, where this is theta, right there, okay? And then the upward or perpendicular components cancel each other out because the block is not falling into the plane or levitating, so we say that the normal force is equal to the perpendicular component of the weight because they cancel each other out, so equal and opposite, and that ends up being mg cos theta after you SOHCAHTOA this triangle here. And then if there's friction involved, so again, frictional force is equal to the stickiness times the force pushing the two surfaces together. Stickiness meaning coefficient of friction, force pushing the two surfaces together meaning normal force, and so that ends up being mu times normal force. So if that makes sense, great. You can kind of draw a triangle and figure it out. If it doesn't make sense, you kind of just want to memorize that, and then you're good to go. So using that knowledge, I'd like you to solve two examples. One example is this. So find the acceleration of a block sliding down a 40-degree inclined plane with a coefficient of friction of 0.2. So you're looking for acceleration. And then in the second example, I'd like you to try to figure out a block slides down a 40-degree incline accelerating at a rate of 1 meter per second squared. What's the coefficient of friction? So we're sort of switching up what information we're given and solving for. So somewhere on here, you got some blank space. Try to figure those out. On page 3 and 4, I have them solved for you, but I'd like you to try to do them on your own. Alright, so page 2, this is describing the loop-to-loop, and when we were doing the lab with the water, swinging the cup of water overhead, I explained this briefly, but here goes a more in-depth explanation. So the cup of water overhead, you realized, hey, as long as I spin it fast enough, it won't fall on me. And so the question is, well, what is that speed, right? You don't want to spin it too slowly. There's you. Okay, so that is spinning overhead. Let's see what I say here. If you go at a constant speed around the loop, you'll feel, so this would be on the case of a roller coaster. If you go at a constant speed around the loop, you'll feel very heavy at the bottom and very light at the top. And so this feeling very heavy and feeling very light, so this is like feel the weight that you feel. And if you were sitting on a bathroom scale in the roller coaster, you'd see the numbers change. That's essentially the normal force, right? It's the force of the seat pushing up on you that makes you feel, whoa, I'm sinking in the seat because I'm so heavy, or oh, I'm floating on the seat because I'm so light. So here goes some generalizations so these are concepts involved in when you're figuring out the speed to just make the loop. So this is what we did with this lab. And two concepts involved in this situation right here is that at the top, weight supplies all the centripetal force. So the normal force of the tracks on the coaster would be 0, just like if you were spinning this just overhead so that it didn't splash out on you, the tension in the rope would be 0 right there. So at the top, what we can do is we can say that the weight equals, and this is mass times centripetal acceleration, giving us a pretty simple formula relating how fast you have to go to the radius of curvature to the acceleration due to gravity. So if I were you, I would write those things in right here with little arrows. You probably know what those are, but minimum speed required to make the loop, radius of curvature, and acceleration due to gravity. Okay, so to help us figure these things out, here's what's going on when you're moving in a circular path around this vertical loop. At the top, the normal force, so this is the force of the tracks pushing on the cart, or in the case of water, it would be the tension in the string, and the weight, they're in the same direction, obviously, and both of these contribute to create the centripetal force. So I would label these quantities here: centripetal force, weight, normal force, and you might even say normal force or tension. So go ahead and write those in. And so here's what I say. This is sort of the concept involved. At the top, weight supplies some or all, in the case of the necessary centripetal force. Normal force provides the rest. So that is kind of saying in words what this says, but this is the situation at the top. And again, centripetal force is going to be equal to mass times centripetal acceleration, which is equal to mass times v squared over r. Okay. So again, please have these things listed, okay? I want to look at your notes and see those there. At the bottom, it's different. Weight always pulls downward, right? But here, the track would be pushing upward, so you would feel very heavy if you were in this roller coaster right here. Tension, when you swung the tennis ball up and down, more tension here, less tension here. So at the bottom, the normal force has to both cancel out the weight and provide the centripetal force. So we can describe that in a formula like here. Normal force is equal to weight plus centripetal force. So these are two relationships. So at the bottom of a loop-de-loop and at the top of a loop-de-loop that will help us. Okay, so in the ensuing 2 pages, I have solutions to those 2 samples that you tried on the first page. So I'm just going to kind of just show it to you, and then you're probably going to want to push pause, take a look. So here was this one, free body diagram, net force mg sine theta minus mu mg cos theta. Hopefully this isn't too messy. So this, oh yeah, I even say it, net force equals this, and that's always the case, and it equals ma. So we solve, and hopefully you got 4.8 meters per second squared. So go ahead and pause if you need to copy that down. And for the second example, drew a diagram, listed the given information, free body diagram. Again, net force equals ma, and so solving gives coefficient of friction of 0.7. Again, a reasonable value. Thanks.